Ladies and gentlemen, good morning. My name is Camilla Ronchei. I am a research assistant at the University of Calabria, and the title of the paper that I'd like to present you today is Fatigue Behavior Assessment of Additive Manufactured Ti-6Al-4V by means of a critical plane criterion. I really would like to thank my co-authors from Italy. The goal of the present paper is to theoretically investigate the fatigue behavior of additive manufacturing AM titanium alloy specimens by means of a critical plane-based fatigue criterion proposed in the past by Carpentieri and co-workers. My presentation consists of the following sections: introduction of the fatigue behavior of AM metallic components under constant amplitude cyclic loading, description of the examined experimental fatigue data, description of the theoretical framework of the Carpentieri et al. Criterion, presentation of the results and discussion, and finally, conclusions. Nowadays, AM is a widespread technology employed to realize complex geometries with a significant reduction of fabrication time with respect to traditional manufacturing methods. Moreover, AM process allows to reduce the weight of the components without joining and welding operations needed when using conventional techniques. Thanks to these advantages, the AM technology has become popular in many industries such as aerospace, automotive, and biomedical. As is well known, the mechanical properties of AM metals are significantly different from those of their traditional counterparts, and these differences are more pronounced in presence of fatigue loading. In particular, AM metals experience shorter fatigue lives in comparison to the same metals produced by means of conventional techniques, due to the presence of both internal defects, porosity and lack of fusion, residual stresses, and high surface roughness, which are material inherent features deriving from the manufacturing process. Moreover, also the anisotropic microstructures of AM metals, caused by high thermal gradients occurring during the building process, strongly affects the fatigue behavior. During service operations, AM metallic components are subjected to cyclic loading. Consequently, understanding their fatigue behavior is one of the most important steps in design process in order to avoid catastrophic failures. In such a context, the present paper is on fatigue failure of AM metallic specimens in order to estimate the fatigue life using a critical plane-based approach. In particular, the fatigue tests examined are related to an experimental campaign recently performed by Molay and co-workers on specimens made of AM titanium alloy Ti-6Al-4V. Such specimens were produced by using a laser beam-based power bed fusion machine with the fabrication process parameters listed in the table on the bottom. The material employed in the manufacturing process was a gas atomized Ti-6Al-4V powered with a particle size range of 15-45 micron. The chemical composition of such a powder is reported in the table on the top. The specimens were built with an orientation of both 19 degrees, named vertical specimens, and 45 degrees, named diagonal specimens, with respect to the build platform. All fatigue tests were performed on thin-walled tubular specimens with the geometrical sizes reported in the present figure. After manufacturing, AM specimens were machined in order to reduce the surface roughness according to the ASTM standard, that is, less than 0. micron. Then, such specimens were subjected to a post-processing heat treatment under high pressure, named hot isostatic pressing, HIP, which allows closing the internal defects and relaxing the tensile residual stresses. Such a treatment, together with above scanning strategy consisting in a hatch rotation of 67 degrees, are able to almost completely remove the inhomogeneous and anisotropic microstructures of the present material. Fatigue tests were performed under both strain control and load torque control modes on vertical and diagonal specimens. The experimental loading conditions consisted in tensile, torsional, and combined tensile-torsional loading with a phase shift beta equal to 0 or 19 degrees, with the fatigue ratio R equal to -1. The parameters of the tensile and torsional Manson-Coffin curves were derived from the uniaxial fatigue data as listed in the table on the top. Moreover, the static mechanical properties derived by means of static tensile and torsional tests are reported in the table on the bottom. The above fatigue tests are hereafter simulated through the critical plane-based fatigue criterion proposed by Carpinteri and co-workers. Before presenting the detailed formulation of such a criterion, some remarks on its application to AM metals are needed. As a matter of fact, the Carpinteri et al. Criterion, originally formulated for conventional metal, that is homogeneous and isotropic, can be applied to the present experimental data, since the anisotropic and inhomogeneous microstructures of the present AM metal were removed by adopting, respectively, a specific scanning strategy and a post-manufacturing heat treatment. Moreover, the presence of both tensile residual stresses and high surface roughness, which are peculiar features of AM metals, are not taken into account in the formulation of the present criterion, since tensile residual stresses were completely relaxed by means of the heat treatment. High surface roughness was removed by machining and polishing the AM specimens. According to the Carpinteri et al. Criterion, the fatigue life assessment is carried out at a verification point, P, located on the specimen's surface. Once the strain state at point P is deduced, the average directions of the principal strain axes are determined on the basis of their instantaneous directions by means of the average principal Euler angles phi with cap, theta with cap, and psi with cap. By adopting the weight function W here reported, the average principal strain axes, 1 with cap, 2 with cap, and 3 with cap, coincide with the instantaneous ones. At the time instant when the maximum principal strain epsilon1 attains its peak value over the loading cycle. Then the orientation of the critical plane, which is the verification plane for fatigue life evaluation, is defined by taking an off-angle delta in the principal average plane 1 with cap, 3 with cap. Rotating counterclockwise the average direction 1 with cap by the off-angle delta, we obtain the normal W to the critical plane. The off-angle delta is assumed to be expressed as follows, where Ni-F is the effective Poisson ratio and epsilon y, a, and gamma a are defined by the well-known tensile and torsional Manson-Coffin equations, respectively. Now let us consider the local reference system PUVW attached to the critical plane. The strain tensor related to both the verification point P and above critical plane orientation can be computed, and consequently the corresponding displacement vector eta is determined. Such a vector is decomposed into a normal vector eta n and a tangential vector eta c. Since the direction of the normal vector eta n is time invariant, the corresponding amplitude in a loading cycle can easily be computed. On the other hand, the direction of the tangential vector eta c changes during a loading cycle, and the definition of the corresponding amplitude is not unique. In the present paper, such an amplitude is evaluated by using the prismatic Hall method. Finally, the fatigue life is assessed through an equivalent strain amplitude together with a unique material reference curve, that is the tensile Manson-Coffin curve. More precisely, the above equivalent strain amplitude is expressed by a quadratic combination of the amplitudes of both the normal and the tangential displacement vectors acting on the critical plane. The number of loading cycles to failure, NF, can be worked out by solving the above equation with an iterative procedure. According to the fatigue criterion here employed, the present figures show the experimental fatigue life, NXP, plotted against the equivalent strain amplitude for vertical and diagonal AM specimens. The blue solid curves are related to the experimental tensile Manson-Coffin equations. A good agreement between experimental and theoretical data is in general observed, since the theoretical results lie very close to the experimental curves, and these hold true independent of the specimen build direction, in accordance with experimental outcomes. As a matter of fact, only 12% and 18% of the theoretical results related to vertical and diagonal AM specimens, respectively, fall outside scatter band 3x. See the blue dashed lines in the present figures. The comparison between experimental and theoretical fatigue lives for both vertical and diagonal AM specimens is shown in present figures, where the solid lines indicate a perfect correlation between experimental and estimated fatigue lives. In particular, the following remarks can be made. For vertical AM specimens, 53% of the results fall within the scatter band 2x, whereas 88% of the results fall within the scatter band 3x. For diagonal AM specimen, 64% of fatigue life calculations are included into scatter band 2x, whereas 82% of such calculations are included into scatter band 3x. Moreover, when the theoretical results are located outside above scatter bands, they are on the conservative side. And now let us move to the conclusions. In the present research work, the fatigue behavior of AM Ti-6Al-4V specimens under both uniaxial and biaxial cyclic loading has been theoretically investigated. In particular, fatigue tests available in the literature have been simulated by means of a critical plane-based fatigue criterion proposed in the past by Carpinteri and co-workers. Even if the present paper represents a first attempt to apply such a criterion to AM metals, the obtained results in terms of number of loading cycles to failure are satisfactory, failing mostly into scatter band 3x. Based on the above results, the Carpinteri et al. Criterion seems to be capable of accurately estimating the fatigue life of also AM metals. However, it can be said that further investigations are needed in order to theoretically take into account the presence of both tensile residual stresses and high surface roughness in the criterion formulation. Thank you for your kind attention.